Hey guys, welcome to the first tutorial of Comp 9417 Machine Learning. Let's jump right into it. Today we're going to be talking about linear regression. So before we start on linear regression, I just want to do a very quick recap of some calculus. And mainly, I think most of you know the simple stuff, but I just want to go through chain rule because it's extremely important for doing what we want to do today, and actually for a lot of machine learning models. So what is the chain rule? Okay, well, imagine you have a function f of g of x. Okay, so this is called a composite function because we have an outside function which is a function of x. So you have two functions in here, and the goal is to take the derivative dx of this function. And the chain rule basically says that, okay, you can differentiate the inside bit first, so g prime of x, and then you differentiate the outside function, f prime, and you evaluate it at the original function. Okay, so this is basically the chain rule, and sorry, I know my handwriting is messy. Hopefully it will get better as I do more and more of these recordings, but bear with me today. Okay, so this is pretty abstract. Let's just do a quick example just to make sure we're on the same page. Okay, so let's pick, what's a good example? Let's say 2x squared plus 3x to the power of 4. Okay, and let's call this thing y. So dy dx is the derivative of y with respect to x. Well, to do this, we need to use the chain rule, right? Because if you look at this, we have kind of an outside function, something to the power of 4, and we have an inside function, which is this thing. Okay, so let's make it really clear. What is g of x? Okay, well, g of x is the inside part. Okay, and while we're here, let's take the derivative of this. Hopefully you can recall calculus rules. So this is going to be 4x plus 3. Okay, and the outside function, well, what does this look like? So it looks like this inside bit, which we call g to the power of 4. So f of x equals x to the power of 4. And so f prime of x, right? I'm just getting all the pieces that we need to do the chain rule in one place. So derivative of x to the power of 4 is 4x cubed. And actually we need f prime of g of x. So f prime of g of x okay, is 2x squared plus 3x to the power of 3, right? So this means just take this guy and plug it in to the argument. Okay, so hopefully this is pretty clear. Okay, so what I'm going to get here, well, let's do the steps. Okay, I'll put this one in green. So g prime of x, well, we already saw that that's 4x plus 3. And this part is 4 times 2x squared plus 3x to the power of 3. Okay, and that's pretty much it. So the derivative of y is equal to this thing. And this is basically the only real recap I think we need to do before we jump into linear regression. Okay. Okay, So sorry, just some technical difficulties. Okay, so I know we've all watched the lecture, but I just want to give a quick recap of what linear regression is. Okay, and we're going to do simple linear regression. Oh, God, my handwriting. Okay, and the idea basically is that you get some data, x, y, and basically in most simple cases, you're going to have something like this. Okay, and the goal of linear regression is to fit a line. Let me use a different color here. That somehow fits the data well. Okay, and so the idea behind simple linear regression is how do we pick this line? Okay, well, if you think about it, this line has equation y equals to a plus bx. Okay, and let's just say this is, let's call this a1, b1, and we'll call this line 1. Okay, so the idea is that we could have multiple lines. So let me pick another color. Okay, let's imagine this line. We'll call this y2 equals to a2 plus b2x, and we'll have a third line. Let's do something silly, maybe this line here, which is y3. Okay, and it's going to be a3 plus b3x. Okay, so we have 3 different lines, and the idea is we want to pick the best line. Okay, so what does best actually mean in this case? Well, if you look at it, okay, y1 has parameters a1, b1, and y2 has parameters a2, b2, and y3 has parameters a3, b3. So best line is going to be the line with the best A and B. Okay, so the idea behind linear regression is we just need to find 2 numbers, A and B, that kind of gives you the best line. Now, if I just look at this plot, I can probably tell that the red line, y1, is probably the best. It looks like it's fitting the data quite well. The green line is a bit worse, and the blue line is really bad, right? Because the blue line doesn't capture anything about the data. So we need an idea of how do we quantify that y1 is the best. Okay, and this is kind of the central idea of machine learning. How do you pick a model, right? And remember, each model is just a set of parameters. And how do you quantify, how do you put a number to that to tell you that it's actually the best model? Well, this is where the idea of a loss function comes in. Okay, and a loss function tells you how bad your model is, right? It tells you how much you're losing. So it tells you if I use model y1, I'm going to get a number. If I use model y2, I'm going to get a different number. And in this case, we're hoping that the loss that y1 gets is lower than the loss of y2. Okay, so we want to see something like that. So let's say L is the loss function of y1 is going to be lower than the loss function of y2, which is hopefully lower than the loss function of y3, because y3 is a really bad model. Okay, so this is just less than, and L is some loss function. Okay, so this should make sense, hopefully, because as you can see, the blue model is terrible, the green model is slightly worse than the red one, and the red one should be okay. All right, so how do we actually do this? How do we come up with a number to quantify this? Well, let me just redraw this thing. Now, here, let's say this is my line, and the question is, what is this line actually telling us? Well, it's telling us that for this value, right? Let's say this guy here, whose real value is y0, and this is x0. It's going to predict this number here. Okay, and we'll call this y hat 0. Right? So basically what I'm saying is that for this data point and this line, the red line, the real value of this point, x0, is y0, and the predicted value based on this model is going to be y hat 0. So hopefully you can see that a good way of measuring how good the model is doing is by looking at this distance here, which is y hat 0 minus y0. Okay, so this is called the residual. Okay, the residual is the error or how bad your model is doing. And each point is going to have a residual. Okay, and the idea behind least squares regression, which is kind of the main way we do regression, is to look at all these sums. Okay, and so these tell you the distances, and somehow use that to quantify how bad our model is. Now, one problem you'll see is that for this guy, right, if I do y hat minus y, okay, well, y hat is the predicted value, so it's going to be here, and the true value is up here. So this number is going to be a smaller number minus a bigger number, so this is going to be negative. And this number down here, well, y hat is bigger than y0, so this is going to be a positive number. So if I just add all of these up, the positive and the negative cancel out. So what we need to do is make sure that we don't deal with any negative values. So we actually look at the squared values. Okay, so here's my loss function. Let me use a clearer color. So my loss function between my y and my y hat is going to be, well, how many data points do I have? Okay, from 1 to n of yi minus y hat I, and I'm going to square it because I don't want to have positive and negative residuals, errors. Okay, so that's why we square things. And this thing here is called the least squares loss. Oh, well, sorry, this is called, my mistake. Sorry, it's not called the least squares. It's called the sum of squares. Sum of squared errors. And it's kind of simple, right? Because we're summing over all the data points, right? For every data point, I'm assuming we have n data points, we're summing over this value, which is the distance, just the vertical distance between the true value, okay, and the predicted value, yi minus y hat I. And we take a square to avoid issues, as I said here, with the negative and positive. Now, if I put a 1 over n here, okay, so if I add 1 over n, then I'm averaging over the errors. And this is called, another word for this is the mean squared error. Okay, so the average squared error. So it doesn't really matter which one you use, just some terminology that you'll see often in the literature. Okay, so hopefully this is clear, and hopefully you can see if we go back to our original example, if we look at the mean squared error of the red line, okay, you can see that this point is quite close, these points are quite close to the line, and so you're going to get really small contributions of error from these guys because, and that means that this sum is going to have small terms, and so you get some big ones, but it's not too bad. So the idea is that it's kind of lying close to all points. But if you look at the blue line, okay, it's going to have huge residuals because it's going to be looking at distances this big. And the idea behind least squares regression is that it penalizes very big differences, because if you look at this big residual, you're taking the square of a big number, which is an even bigger number. So the loss for the blue line should be huge compared to the loss of the red line. Okay, so hopefully this is kind of making sense. And most of machine learning, well, all of machine learning really is basically just here. We pick a model, we figure out what the parameters of the model are, and then we pick a loss function to tell us how good our model is, and then we try to, so this is the next part, okay, so let me just copy what we had. So mean squared error is the average, I equals 1 to n, yi minus y hat I squared. Now, this is any prediction. It doesn't need to be linear regression. In this case, we're doing linear regression, but this actually works for anything. So y hat is just the predicted value. Okay, so it could be a linear regression, which we're doing today, but it could also be a neural network, which we'll do later on. And it could also be a random forest. So the idea is that this is going to tell you how good your model is doing, regardless of how you come up with y hat. Okay, so hopefully that's kind of intuitive. This is just a distance that quantifies, how good the model is. Now, the last step in machine learning is picking. So pick parameters that give best model, which means lowest MSE. Okay, now if you recall, in our case, we're doing simple linear regression, so y hat I is equal to a plus b xi, right? So we need to figure out the best a, b that are going to give us the lowest MSE. So how do I write this? I'm going to write this, I want the a hat, b hat, which are equal to the arg min av of 1 over n, I equals 1 to n, yi minus a minus b xi squared. Okay, so let me explain this notation. You'll see a hat here, okay, and this is basically just a way of telling us which are the best parameters. So the best parameters, a hat, b hat, are the ones that minimize, okay, they're the arguments that minimize this guy, which is the mean squared error. And under the minimum, I've put a and b just to explain what we're trying to minimize this guy with respect to. Okay, so we want to pick A and B to give us the minimum of this, and the particular A and B, the arguments that do that minimization, are called A hat, B hat. And I just want to show you guys this notation because even if you're not really interested in the math, if you're interested in machine learning, you'll see this notation everywhere. And as I said, in this case we're doing linear regression, but this could be anything. As you can see here, I just substituted y hat I for the simple linear regression case. Okay, well, now we have our 3 steps. So let me recap our 3 steps. Pick a model, pick a loss function, and then third is find a model that minimizes the loss function. Okay, and that's pretty much every single machine learning model you'll see is basically just these 3 things. All right, so let's actually do the fun stuff, which is minimizing this guy. All right, well, so you've seen the derivation of the tutorial, but I'm going to cover it here just for clarity because it's an extremely important derivation. Okay, so this is called the least squares derivation. And I should say before we do that, okay, what does it mean to minimize a function? How do I take the argument of something? Okay, well, let's do a simple example. Let's take a function x squared. Okay, I want to find the argument that minimizes x squared, and so the minimum is going to have an x under it, and I'm going to put an x hat is equal to the argument of x squared. Okay, so how do I minimize x squared? Well, one way to do it is just to draw a picture of x squared. So hopefully you remember that x squared looks like this, and obviously the minimum is going to be at 0, right? But most of the time you can't just plot a function easily. So what you could do is just use calculus. So we do f of x equals to x squared. We take the derivative. Okay, and then we make the derivative equal to 0. And we solve. In this case, 2x equals 0, so x hat is equal to 0. So this is the special x that minimizes this function x squared. Okay. Okay, so what if I'm looking for the x hat argument of 2x plus 3 squared? Okay, this is slightly more difficult, but it's still pretty simple, right? It's still the same idea. Okay, well, we have our f of x. And to find the derivative of f of x, okay, well, recall we need to use the chain rule. Okay, so revise what we did at the start of the tutorial, but I'll just do it quickly here. It's going to be 2 times 2x plus 3. And we're going to make this equal to 0. And if you solve for x, you'll get that 2x plus 3 equals to 0. So x hat is equal to minus 3 over 2. Okay, and that's basically the idea. Okay, so we want to apply this simple logic to find the best regression line. Okay, so let me start a brand new page. Okay, so this is our loss function, LAB is equal to 1 over n, I equals 1 to n, yi minus a minus bxi squared. Okay, so here I'm just making some quick assumptions that I have n data points, so our data set D is equal to some points, xi, yi, for I equals 1 to n, okay? And I want to use these guys to figure out the best A and B, okay? So, and I'm using L here for a loss function. Okay, well, we have two parameters, right? A and B. So we need to take the derivative of L, the loss, with respect to A first, and then B. Okay, so let's do the first part. So we want to take the derivative with respect to A. Okay, well, let's look at this thing. Hopefully you should see that this is just a simple application of the chain rule, because when you take the derivative of 1 over n, I equals 1 to the power of n, sorry, yi minus a minus b xi squared, what happens is that the derivative can be pushed inside the sum, right? The derivative of a sum, a finite sum, is just the derivative of each individual term. Okay, so 1 over n sum d dA yi minus a minus b xi squared. Now, this makes life real easy because this inside guy is just a very simple differentiation using the chain rule. Let me go back to blue. So it's going to be 1 over n, the sum. So I'm going to drop the notation here I, but you should just keep it just because it makes my life a little bit easier at the moment. Okay, so how do we differentiate this guy? We use the chain rule. So we're going to get a negative from the inside here, right? This is differentiating the inside part with respect to A. We're just going to get a negative from the A, so negative 1. Then this 2 comes down, and then we multiply by the original function. Okay, and recall what we need to do to minimize is make this equal to 0, right? That's what we just did to find the minimizer. Okay, so let's see here. Let's try to simplify things. Well, let's just look at the constants first, right? So you can see here we have a 2 and a 1 and an n. These are all constant values, so we can just get rid of them all, right? Because there's a 0 here. So the idea is that I can multiply this side by n and this side by n. And these n's cancel out, and 0 times n is still going to be 0, so it's 0. So the idea is that when you have a minimization, you can pretty much just get rid of all the constants. So this line implies I'm still going to have the sum, can't get rid of the sum, but the 2, the 1, and the negative value are all just constants, so I can get rid of them, and I'm left with yi minus a minus bxi equals to 0. Actually, sorry, that I just made a quick mistake. Let's keep the 1 over n, okay? But we can still get rid of the 2 and the 1. So ignore what I said here. You can do this, but let's just leave it in for now. Okay, so this line implies this line. So all I did was get rid of these guys, and I kept the 1 over n. Okay, now let's just open the sum up a little bit. So this is 1 over n sum yi minus 1 over n sum a minus 1 over n sum b xi. Okay, this is I equals 1 to n, I equals 1 to n. And this is still going to be equal to 0. Okay, so what do we have here? Well, if you look at this sum, this sum here, you'll see that the a doesn't have an index I, right? So you don't need to keep it in the sum. You can actually take it outside. So I'm going to put an a here. and I'm going to erase the A inside here. And the same thing with this B, I'm going to take it outside. Okay, because the B doesn't have a, let me just make it really clear what I've done here. Okay, I took the A outside here, I'm going to have a 1 inside, and I'm going to take the B outside here, and I have a 1 there as well, so 1. Okay, now I can do that because, you know, the A and B don't actually depend on the index I. Okay, so what does this line imply? Okay, well, first of all, this A over n times the sum of 1. Let's just do a quick calculation here. Okay, hopefully remember that the sum from 1 to n is just n, right? Because I'm just counting 1 n times, and I have a 1 over n outside. So all I'm going to get, sorry, from here, I have a 1 over n outside. All I'm going to get is a minus a here. Okay, so this sum becomes an a. What is this guy? Well, this guy is just the average yi, right? It's the mean yi. And the way we write this is y bar. And similarly here, if you look at it, I'm going to have a b, and what is this guy? It's 1 over n times the sum of the xi's. So this is just x bar equals to 0. Okay, so anytime you see this notation, this is really important. Let me just write it here. Anytime you see this notation, this means the average. Okay, 1 over n times the sum of each fi. What if I see this guy, fg, with a big bar on top? Well, this just means 1 over n, I equals 1 to n, fi gi. So the sum of the products. Okay, so going back to our line here. Okay, well, the whole point of this thing is to get an expression for a. Okay, so let's get a. Let's move it to the other side. We get a is equal to y bar minus b x bar. Okay, and let's just put a box around that expression. Okay, so are we done at this point? Do we have an expression for a? The answer is no. Okay, and the reason is, if you look at this expression for a, we still have this dependence on b, right? And b, we don't actually know it. The whole point of this exercise is to pick a and b to minimize this guy. Okay, so we need to basically do this whole thing again for b, and then plug the result of that into this expression, and then solve. Okay, so let's do that. Okay, so step 2 is dl db, okay, which means we're going to have 1 over n, the sum d of db of the inside stuff, which is yi minus a minus bxi squared. So it's very similar to what we just did before, except now, okay, if you do the chain rule, the b has an xi, okay? So what we're going to get is, okay, hopefully you can see the pattern now. We're going to get a negative xi, right? Because when we differentiated with respect to a, the a just has a negative 1 at the front. But with respect to b, b has a negative xi, so we need to actually take the xi out. We're still going to get a 2 because this 2 is coming down, and what we get in here is the same. Yeah, and we set this equals to 0, okay, because we want to minimize. Okay, so let's simplify this again. Again, I can get rid of the 2 because I have a 0 here, so I can just multiply both sides by 1 over 2. I have a negative, I can get rid of that. I can't get rid of the xi. Okay, and we're going to keep the n, even though we can get rid of it. And let me just expand this out. Okay, so I'm going to, in the first one, I'm going to have xi, yi. In the second term, I'm going to have, well, the a is by itself, but it's going to get multiplied by the xi. And the b, just like before, comes outside. Okay, but now the xi gets squared. And we make this equal to 0. Okay, so it's very similar to what we just did before, except we have this added xi term that makes things a little bit more difficult. Okay, now what is this expression? Well, this is the average of xi, yi. So in our notation, that makes life much easier. It's just xy bar. And this guy is just going to be the same as before, x bar. And this last one is minus b. Well, this is the average of the xi squared. So this is going to be x squared bar equals to 0. Okay, so be careful. X squared bar is not equal to x bar squared, right? They're different. So just make sure where you're putting your bar, or it's clear where you're putting your bar. And if we solve for b now, okay, just a bit of algebra. Okay, we'll get this expression over here. Okay, so let me just go back to the previous slide where we showed a is equal to this. Okay, let me just put it here as well. Y bar minus b x bar. Okay, and now we have this expression. Okay, so we have our b, which depends on a, and we have our a, which depends on b. These guys are really important. They're called the normal equations. Okay, and if you've done linear algebra, you've heard this term, but it's basically how we solve a system of equations. We have a system of equations here, and this normal equations is what's used in the literature to describe these equations. Okay, so how do we solve? How do we actually solve for b? Because we don't want to have b to be a function of a, right? We don't want it to be b is equal to f of a. We want it to be b is equal to just some function of the data, x and y. Okay, so it's pretty simple. All we do is we take the a and we plug it in to the b. Okay, so let me just write it here. B is equal to x y bar minus, well, a is going to be y bar minus b x bar over x squared bar. Now this is just algebra at this point, but you can expand. Okay. Now you have b on the right hand side, the left hand side, you can move it over. You should get x bar squared over x squared bar equals to xy bar minus x bar y bar and over x squared bar. And then if you solve by dividing both sides by this, and you simplify a little bit, you'll get a nice expression, which is just x y bar minus x bar y bar over x squared bar minus x bar squared. Okay, and so now we have an expression for b. So this is what I meant by just wanting to have an expression for b in terms of x and y. Okay, so now we have this kind of form. We don't want to be dependent on anything else except for the data. And to solve for a, well, that's going to be easy because once you have b, you just plug it in there and you get an expression in terms of just x and y. So this is really all we need to solve the problem. Okay, so that is called the least squares derivation for simple linear regression. Now, let me just take a quick minute to explain why is this nice? So remember, here's our line. This is y equals to a plus bx. So b, and this is our x, this is our y. B is equal to the slope of the regression line. And we just showed that b is equal to x y bar minus x bar y bar over x squared bar minus x bar squared. Okay, so that's actually just, it's useful in machine learning or in statistics in general just to try to interpret what this means or what we're working with to make sense of it. So let me just take a quick aside. Remember the sample covariance. Okay, what is the sample covariance? It's 1 over n minus 1 times the sum of xi minus x bar, yi minus y bar. This is called the sample covariance. It tells me, it kind of tries to tell me, how related x and y are. Okay, this is xi. Okay, now if I just expand a little bit, okay, I'm going to expand by opening up the brackets. Xi times yi. Sorry. Xi times yi. Let me just put a bracket here. Minus xi y bar minus yi x bar plus x bar y bar. Okay, so all I did was just expand the brackets. Now, what is the first term here? Okay, well, we know that if we had a 1 over n, this would just be x, y bar. But here we don't have a 1 over n, we just have the sum. So the trick is we put an n and then x, y bar. Right? Just let me explain it here. Okay, recall that f bar is equal to 1 over n times the sum fi. Okay, so if I put an n here, it's like getting just the sum. Okay, so all I'm saying here is that for this expression, because I don't have a 1 over n at the front, I can just put an n and still use the notation x, y bar. Okay, what about this guy? Okay, well, the y bar doesn't have an index in it, so it becomes y bar. Take it outside of the sum, and I'll just have an xi. And same thing here, x bar comes out the front, because it doesn't have an index I, and the yi stays in there. And neither of these guys has an index. These are just x bar, y bar, so I can take them both out. Okay, this is still going to be I to n. Now it's just going to be a 1 in here. Okay, so in this step I just took the summation to each of the terms and simplified a little bit. I'm going to simplify some more. Okay, this stays the same, n x y bar minus, well, what is the sum of xi? Well, using the same trick, this is just going to be n x bar, right? So I can write n x bar y bar. Same thing here, the sum of the yi's is going to be n y bar. So again, n x bar y bar. And what's going to happen here? Well, this sum is going to give me n. So I'm going to have n x bar y bar. Okay, so something nice happens here. Basically, this and this cancel out. Okay, minus n x bar y bar plus n x bar y bar. So all I'm left with is this front part. Okay, let me take the n outside of the brackets. What I'm going to get inside the brackets is xy bar minus x bar y bar. And hopefully you should see that this inside the brackets is exactly the same as the numerator of the slope of the regression. Okay, so why is that interesting? Well, let's add one more piece of information. What is the sample variance? Okay, how do I compute the sample variance? Well, it's 1 over n minus 1 times the sum of xi minus x bar squared. Okay, now if you do the same kind of calculation, but on this guy, what you're going to get is n over n minus 1. And hopefully you can guess the answer. It's going to be x squared bar minus x bar squared, which is exactly the denominator, except we have this extra n over n minus 1 factor. Okay, so why is that interesting? Well, let me just write it up here. Okay. I'll use red. Okay, so this thing, right? It doesn't matter if I multiply by n over n minus 1 in the numerator and the denominator, because they cancel out. Right? These two are equal because these guys cancel out. So in other words, we're saying that the regression slope is equal to the sample, so sample covariance x, y over the sample variance of x. Okay, sample covariance of x, y, sample variance of x. So why is that interesting? Well, it's basically just saying that the slope, if the covariance of x, y is positive, right, so they're positively covariant, they're positively correlated, then then the slope is going to be positive. So that makes sense, because if we observe, when x increases, y also increases, the covariance is going to be positive. So you'd expect a positive slope. And if you saw a negative trend, so something like this instead, then we'd expect a negative covariance, so the slope would be negative. Okay? And basically it's just saying that the slope is controlled by how strongly they move together in the same direction. And we divide by the sample variance because we want to normalize by how variable x is. So x could be extremely variable, and so we just need to basically normalize by the variance when we're shifting, when we're shifting the y value. Okay, so it's nice to have this interpretation. Now, why did I focus on the slope and not the intercept? Well, the intercept isn't really that interesting. And the reason is, the intercept of a line doesn't really tell you much, because you can always you can always normalize your data at the very beginning and make the intercept equal to 0. So usually when we do regression, we're really just interested in the slope parameters. It's important to get the right intercept, of course, but it's not very meaningful to interpret this too much. Okay. All right, so that is the least squares derivation. So I know it's already in the tutorial notes, but I just want to go through this derivation quite slowly. And I want you guys to basically repeat this derivation a few times because basically a lot of machine learning can be learned just by understanding the steps in this derivation. All right, so now we have our least squares derivation. But one thing you might ask yourself, is this is a really simple model. Okay, we have one y, we have one x. Well, you're always going to have one y, but you only got one x, and that's not really what machine learning is about. Machine learning is about making sense of very large data sets with lots of different features. So what is the point of doing this model? Okay, well, let's do something more interesting. Let's look at let me go back to blue. Red is only for really important stuff. Let's look at multivariate regression. Okay, what does multivariate mean? Well, before I used the word simple, because I only had one value x, now I'm going to have multivariate regression. Okay, so what is multivariate regression? Well, let's look at the example of y is equal to house prices. Okay, now when you're looking at a house price, you might have more than one feature. Okay, you might have the number of bedrooms. Okay, the number of bathrooms. You might have the location, like the suburb, for example. What else? You might have the square footage, square feet, and you can have a lot of information, let's say x1 to xp. So if you think about it now, we can't really draw it right because you're going to have your y, you're going to have your x1 axis, but then you're going to have your x2 axis, you're going to have your x3 axis. You can't really draw 4 dimensions, but you get the point. Now you have a p-dimensional problem, not just a one-dimensional problem. And this is called multivariate regression. And this is kind of what you're going to be doing in real life, right? For every problem, you're going to have multiple features. So these guys are called, well, they have a bunch of names. They're called predictors, right? Because they help you predict the y. They're also called features in machine learning. More commonly, they're called features. In statistics, they're called predictors. In statistics, they can also be called the covariates. Okay, and they're also called the independent variables. Independent variables. And the y value is called the target or the dependent variable. Okay, so you can think about, y is called dependent because it depends on the independent variables, the x's, or y is the target that we use the predictors or features to predict. Okay, so what do we do in this case? So if you pause the video now and just have a think about it, I actually already gave you the answer because in the previous few slides, if we go back to this slide here, okay, I said all of machine learning kind of comes down to these 3 steps, right? You pick a model. Okay, so we changed the model now. We had simple linear regression. Now we have a multivariate linear regression. We pick the loss. Well, here we had mean squared error, but we can actually pick the same loss. That's a very common loss function to use, even for deep learning. And then we need to find a model that minimizes the loss. And so these steps are not really going to change. So let's stick to the same loss. So let's write out the mean squared error for this problem. Mean squared error is going to be 1 over n times the sum yi, that's the true y, minus the y hat I squared, right? So what's changing? Well, now we have a model with p predictors. So if you just imagine in 3 dimensions, okay, if I just, let me get rid of this x3. Okay, so imagine I had this problem, I had just two features and one y. What does my regression line look like? Well, it's not going to be a line, it's going to be a plane. It's going to look like this. It's going to be, let me see. It's going to look like this, like a piece of paper. And the data points are going to be, scattered in 3-dimensional space. And but the basic idea is still the same, right? We're still going to measure the distance from the point to the plane. Okay, we're still going to take the vertical distance of each of the points to the plane. But what is the equation of this plane? What is the equation? Well, it's y hat equals to well, let me just use a better notation. Let me use the W notation. W0, because before I was using A and B, but here I'm going to have, A, B, C, D, E. I don't want to do that. I want to use W0 for the intercept plus W1 x1 plus W2 x2. So this is my line, or my line in 3 dimensions. Now, one thing I should say here quickly, I've just noticed that I've kind of mixed the notation a little bit. I use the hat here. Y hat is the predicted value. But I also use the y hat notation here to tell you what the optimal parameters are. They're not exactly the same, so just be careful. I know it's an abusive notation, but you'll see them in both places. You'll see them for the fitted values, but you'll also see them for the solutions to optimization problems. Okay, so hopefully that's not too confusing. Anyway, so let's come back to our problem. Now we have an equation of this line in p dimensions, okay? We're just going to change the predicted value here. Well, it's going to be W0 plus W1 x1 plus W2 x2 plus WP xp, whole thing squared, right? All I'm changing is the model, and my model now is this multivariate linear regression. And now I have p plus 1 parameters. So step 3, step 3, find a model that minimizes the loss, is going to look slightly different, but very similar. Well, slightly different. We're going to have W hat 0, W hat 1, but we're also going to have all the way up to W hat P, and now we're minimizing 1 over n yi minus W0 minus W1 xi minus all the way up to WP xp squared with respect to W0, W1, W2, W3, all the way up to WP. Okay, so this is why I said this was so important, because we've changed the model, we've made it a lot more advanced, but the basic idea is exactly the same. You actually know how to solve this. All you're going to do is, well, let's go back to here, right? How did we solve this problem? Well, we took the derivative with respect to A, then we took the derivative with respect to B, and then we got the normal equations, right, here, and then we solved. So here, all you need to do is solve for dl dw0 equals to 0, dl dw1 equals to 0, all the way up to dl dwp equals to 0. Now we're going to have p plus 1 normal equations. Okay, so my point is that it's still called the normal equations. It's still the same calculus. However, at this point, you should kind of notice that this is going to be really, really tedious, right? It's going to be really annoying. I've got to take a derivative, p plus 1 times. I've got to do p plus 1 calculations, and then I've got to substitute things into each other. And, it's going to get really, really messy. And this is where vector calculus and linear algebra kind of come to the rescue. So let me introduce some new notation. And, this is going to be slightly beyond the scope of the course. But if you're really interested in machine learning, there's really no way of getting around the the kind of idea that we need matrices and vectors. Okay, so let me, instead of writing w0, w1, w2 to p, I'm going to just introduce this w vector, which is going to be a column vector. Okay, so basically I'm just going to collect all the parameters into this one w, and I'm going to use this notation, belongs to rp plus 1. So this is just saying that this is a vector in dimensions p plus 1, right? We have the intercept w0, and then we have p slopes for each of the p features, okay? All right, then I need to also introduce a big Y. Okay, and you'll see the notation, sometimes you put an arrow at the top of these guys. I'm personally not going to use that, but you will see that sometimes. Then I'm going to stack all the Y's. Now this is going to be a vector in Rn, right? This is Y1, this is the observed Y's. And I'm going to also introduce xi. I'm going to the notation is going to be a little bit abused here from what I put in the previous slide, but let me just write, this is going to be the ith observation. So it's going to be it's going to be a vector with a 1 at the top, and then xi1, xi2, all the way to xip. And this is obviously going to be a p plus 1 dimensional vector. Okay, so why? Let me just explain why we have a 1 at the front. Well, if you think about it, the ith observation, okay, so if you go back to our house problem, the ith observation is going to be a house. It's going to have a certain number of bedrooms, certain number of bathrooms, a suburb, a square footage, etc. So this vector is collecting the information for a single house. So xi1 is going to be the number of bedrooms for the ith house, xi2 is going to be the number of bathrooms for the ith house, etc. Now I need a 1 because I want to multiply this guy with w, and so w0 is going to get multiplied by 1. And you should recall that the equation is going to be w0 times 1 plus w1 times x1. Okay, so that's why I need that 1 to make sure that w0 is by itself. Okay, and then, so hopefully, I mean, even if this is a bit confusing at the moment, just bear with me because we'll go through it very slowly. Now, X is going to be a big matrix where I'm basically going to collect all of the observations. So the X1, I'm going to take the transpose. Okay, so I'm going to take all the observations and I'm going to transpose them. I'm going to stack them into a big matrix. And you should note that this is going to be n by p plus 1. Okay, so what is okay, let me just give you an example. If I have a vector v which is equal to 1, 2, then v transpose is just the row vector 1, 2. So all I'm doing here is stacking. So the first row is going to be x1, 1. It's going to be 1, x1, 1, x1, 2, x1, 3, all the way to x1p. So the first row is for the first observation. The second row is going to be for the second observation, so x21, x22, all the way to x2p, and then we're going to keep going like this for all of them. The last one is going to be the nth observation, xn1 to xnp. Okay, so this is why it's going to be n, so n rows by p plus 1 columns. Even if you're not that interested in matrices and vectors, just if you're working in NumPy or Pandas, you're going to have to deal with data frames, and you need to know the shapes of things. So this is a good thing to keep in mind. Okay, so why is this going to make our life much easier? Well, the model y hat I, right, is going to be equal to, this is the prediction for the ith point. It's going to be w0 plus w1 xi1 plus all the way up to wp xip, right? This is the prediction for the ith observation. I'm using this notation because now we have, for ith observation, we have multiple features. But basically this is the output of the line, right? Now how do I write this in a much simpler way? Well, this is just going to be the dot product, or the vector product of W transpose and Xi. Okay, and you can also write it as Xi transpose W. It doesn't make a difference. They're both the same thing. So just recall, if we have another vector, we have V here. Let's put another vector Z. Let's make this 3, 4. What is V transpose Z? Okay, well, you just multiply the first number here and the first number here. So 1 times 3 plus the second number times the second number, 2 times 4. Okay, so the idea is quite simple. I'm just making my life a lot easier. Instead of writing the whole summation out, I'm just going to write it as a dot product, W transpose Xi. Okay, so now let me go into a new page. Recall the loss function. Now the loss function is a function of the p plus 1 parameters. I can write the whole thing as just the loss function of the vector W is equal to 1 over n, I equals 1 to n, of yi minus the predicted value of yi, which I just said that we could write as W transpose Xi squared. Okay, and that's the beauty of using matrices and vectors. It makes the notation so much cleaner. Okay, and instead of writing all these parameters out each time, I'm just keeping them all in one combined location. Okay, now I'm gonna rewrite this whole thing in terms of the matrix X. Okay, and you'll see this. Let me actually introduce you to the notation, even though it's going to look a little bit confusing at first. You'll see this notation. And this is exactly the same as, this is called the 2 norm. 2 norm. The brackets. And so, for example, the 2 norm of a vector squared is equal to just the sum of the elements squared. Okay, and this is also equal to the same thing, y minus xw transpose times y minus xw. These are the same. These three are all the same thing. The idea is that we want to, I basically just want to get rid of the summation here. I want to keep it really clean and just put it and do it all in terms of matrix calculation. And basically, you'll see this notation a lot in the machine learning literature, so I'm trying to expose you to as much as possible early on. And so you can use this tutorial as kind of a reference for the rest of the, or for a lot of the machine learning that you do. Okay. You can prove to yourself, hopefully, that these guys are equivalent. All you need to do is basically just expand xw. Okay, and then you'll see that each row is x1 transpose w, x2 transpose w, xn transpose w. Okay, this is the big matrix x times w. And so when I take the vector y minus this, okay, all I'm getting is the inside term. And then when I multiply by itself, I get the squared and the sum. Okay, that's the idea. Okay, why do I want to talk about this? Well, now the idea is I want to find w hat, which is equal to the argmin of w of the loss function y minus xw transpose y minus xw. Okay, well, let me just rewrite this guy as 1 over n. So this is a function of w. Okay, so you may not be that experienced with matrix calculus or matrix algebra, but it's very similar to just normal algebra. So how do I do this? Well, I can just expand this bracket. This is going to be y transpose y. So we don't have squareds when it comes to vectors. We have y transpose y. Then the y transpose gets multiplied by this, so minus y transpose xw. Okay, then we do the same thing, minus, so remember xw transpose is equal to w transpose x transpose. Okay, you transpose each of the inside guys, then you switch the direction. Okay, and then finally, we do the xw transpose times xw, and you're going to get w transpose x transpose x w. Okay, and now let me just simplify this a little bit. Now, if you look at these two values here, okay, let's just look at y transpose x w minus w transpose x. Let's put a square around this so we don't confuse things. Y. Okay. I can write this as y transpose x w minus y transpose x w transpose, right? Because if you transpose this guy, okay, you'll just switch the order and you'll transpose everything, you get this. Okay, now this is actually equal to 2y transpose x w. Okay, why is that? Well, because if you think about it, what is y transpose? It's a vector in n by 1 vector. X is n by p plus 1. Oh, sorry. Y transpose is 1 by n. And W is an RP plus 1 vector. Well, P plus 1 by 1. Now, what happens if I multiply y transpose by x? Well, I'll get a 1 by n times an n by p plus 1. So that's a 1 by p plus 1. Okay, and then I multiply by w, which is p plus 1. So what I get in the end here is a y transpose x. W is just a 1 by 1 matrix. So what that means is just a scalar, right? And if I transpose a scalar, it doesn't make a difference. 2 transpose is just a number, it's just 2. So I can just combine these guys, okay? So what I get here is 1 over n y transpose y minus 2 y transpose x w plus w transpose x w. Okay. Now we have our expression for the loss. Sorry, I shouldn't call this f, I should call this L. Okay, now we want to differentiate just like before, dl dw. Okay, now what happens when we differentiate the first term? Well, that has no w's in it, so we'll just get a 0. So we'll leave the 1 over n. We'll get a 0 in the first term. Okay, how do we differentiate this guy? Okay, well, sorry, we should ignore this. Okay, well, a vector calculus is very similar to just normal calculus. So how do I differentiate cx? I just get left with c. Okay, but when it's a vector, I'll actually get c transpose. Okay, so what happens here is that this is the coefficient, this is the thing we're differentiating with, so what we get left with is 2 times the transpose of this, which is x transpose y. Okay, so it's very similar to just standard calculus, except that instead of just getting c, we get c transpose. What about this guy, w transpose c w? This is just like having c w squared if we were dealing with normal numbers, with single variable calculus. And how do we do that? Well, it's just 2c w. So here we're going to get actually 2 c w as well. Okay, so here in our case, x transpose x is the c. We're just going to get 2 x transpose x w. I don't know why I switched colors. I'll go back to blue. And we're going to make this equals to 0. Right, because we want to minimize. Okay, now, if you push this guy to the other side, and you get rid of the constants, the 2's, and you get rid of the n, what you're left with is x transpose x w is equal to x transpose y. And how do we get rid of the x transpose x? Well, we can take the inverse. So we get w equals to x transpose x inverse x transpose y. Okay, and this is a really important formula. It's called the least squares solution, least squares estimator. We can put a w hat, you'll see the hat, because this is the optimal solution. But basically, why I wanted to show you this is because in most of machine learning, you'll be dealing with matrices. Not so much in this course, but it's really just important to get exposed to it and just to see that there's really not much to it. It's not very difficult, and actually it's actually much faster than doing the original way, which we just did earlier in this tutorial. So let's do a simple example. Okay, let's take p equals to 1. This is simple linear regression again. Okay, and let's recall the least squares equation is x transpose x inverse x transpose y. Okay, now when p is equal to 1, what is our x matrix? Well, it's going to be 1, x1, 1, x2, 1, xp, right? Because p is equal to 1, so we only have one feature. So this is the first house, but we're only looking at the number of bedrooms, right? And, you know, this is going to be a matrix in n times 2 dimensions, right? P plus 1 is 2. And y is still going to be the same thing. It's going to be an n-dimensional vector. W is still going to be, well, W now is just going to be vector W0, W1. It's going to be a 2-dimensional vector. And what I'm trying to do here is to show you that this equation here is going to give you exactly the same answer as what we did before in the simple linear regression, because this is the p equals 1 case. So let's just compute this value here. Okay, so let's do that. So first step is, what is x transpose x? Okay, well, x transpose is this. I'm going to flip the matrix. Okay, and then multiply it by itself. To get this. All right, so let's figure this out. This guy. Let me use a different color just not to make things really messy. This guy is a 2 by n matrix. This guy is an n by 2 matrix. So the result is going to be a 2 by 2 matrix, right? Because when you're multiplying matrices, the inner dimension has to be the same, and then the resulting dimension is going to be the outer dimensions, 2 by 2. Okay, so what's going to go in the, so this is going to be a 2 by 2 matrix. Let's figure out what's going to go in the top part here. Well, it's going to be 1 times 1 plus 1 times 1 plus 1 times 1. So we're going to get 1 times 1 n times. So all you're going to get up here is just an n. Okay, so it's going to be multiplying this row by this column and adding it all up. For this guy here, right, we're going to take the first row, multiply by the second column here. So what you're going to get is n x bar, right? This is just going to be the sum of the xi's, because you're just taking the first vector, the first row of the first matrix here times the second column. Okay, what about this guy here? Well, this is going to be exactly the same thing, because it's going to be the second row times the first column. So again, nx bar. And finally, the 2 by 2 element is going to be the second row times the second column. So that's going to be nx squared bar. Okay? So let me just clean this up a little bit. Okay. All right, so now we have our x transpose x, but we actually need the x transpose x inverse, right? So we need to actually invert this matrix. Okay, so let's just do a quick aside. If I have a matrix, A, which is going to be a 2 by 2 matrix, what is the A inverse? Okay, hopefully you remember from your previous math courses, it's going to be 1 over AD minus BC, and then the inside matrix gets flipped. The diagonal line gets flipped, and then the off diagonals get multiplied by negative. Okay? So if you don't, just make sure you recall this. So the inverse of this guy, we're just going to apply this rule, is going to be it's going to be 1 over, I'm going to skip a few steps here, but it's going to be 1 over n squared x squared bar minus x bar squared times n x squared bar minus n x bar Okay, so this is our inverse matrix. And the last piece that we need is the x transpose y. Okay, now hopefully you can show that this is just going to be n y bar n x y bar. Okay. I want to skip a few steps because I want you guys to try to do this as an exercise. And finally, w, right, is the x transpose x inverse x transpose y, which is equal to, well, why don't you guys do it? But you should be able to show that what you get is exactly the W0, W1 hat that's equal to the A hat, B hat that we got before in here. Here. Okay. So the point of this exercise was that I wanted to show you that we could use this formula to get exactly the same result as before. Okay, and that's why this is a much more general result and much more interesting result for realistic problems. Finally, I just want to add a note about how to do this in practice, and I'll just pause the video and start up again in Jupyter. Hey guys, to end up with for this tutorial, I just wanted to add, so you already have the lab. I want you guys to go through that by yourself because I think it's a bit more useful than me just kind of demonstrating code. But I did want to write up this particular quick notebook to kind of illustrate a bit more about the matrix stuff that we saw. So in this notebook, and I'll send it to all of you, what I'm doing is basically just deriving what we just saw over here. Okay, so I'm just generating some data. I'm plotting the data. Okay, and then I'm generating basically exactly what we did here, but I'm doing it in NumPy. Okay, so I want you guys just to get used to this notation. I've already kind of written, just make it bigger. I've already written some LaTeX here just to show you exactly what's going on, but x transpose x inverse, x transpose y, and then the least squares estimate, right, is this thing, x transpose x inverse, x transpose y, and oh, I'm sorry, I think I've made an error here. I think we can get rid of this. Okay, I'll make sure to send you guys the right thing. Okay, so we got 15 and -1, so that's my intercept and slope. And again, I've just made it really clear here that this is very similar to what we did at the start, and I've derived it from by hand using the original equations that we used, these equations here. Okay, so again, I just want you guys to be really careful, really clear on why they're the same thing. Okay, and finally, you obviously don't do this in real life. You don't code it up every time from scratch. What you do is you use a package. So scikit-learn has the linear regression object from the linear model collection, and basically you would just do it like this. Okay, so you would fit your model on the X, give it the targets, and it would just print things out for you. Okay, so in this notebook, you've got 3 ways of doing the same thing. So let's call this least squares 3 ways. Okay, and I just want you guys to be comfortable with all 3. And here finally, I'm just plotting the fitted line that we get. Okay. I'll see you guys during the office hours during the week, and if I don't see you there, I'll see you guys next week.